Okay, all right, welcome back, everyone. This is Tuesday. I'm sorry, this is Thursday, April the 2nd. Today we are going to have two lectures, trying to finish up the section on chapter on optical properties. We're going to first finish up the optical constants, and then we are going to look at various processes regarding to the light response, response of the material to light. Okay, there are many things, and then we're going to have a quiz later today. This will be covering the lectures on dielectric properties. Okay, and then next week, Tuesday, we're going to talk about LEDs. These are one of the two kinds of optoelectron devices we're going to talk about. And then on Thursday, we'll also talk about solar cells. So two different ways of converting between electrical energy and optical energy. And then we're using the remaining time, we'll do a quicker review. This leads us to an exam, the final, well, I shouldn't say the third in-class exam, which will be done on Tuesday, April 14th. And by the way, we will still have a quiz on April 9th, and that will actually be our last quiz this semester. And that quiz will cover things we talked about this week, optical properties. And then after that third exam on Tuesday, we'll use the Thursday lectures to talk about magnetic properties. There will not be a quiz that week, but we'll just use the two full lectures to talk about magnetic properties. And then the last week, April 21st, we'll do a final review everything we have talked about so far. And then we will have a final exam on April 30th during the normal assigned time. It's not a good time, 7:30 to 9:30, so you have to come up, get up early. This is, unfortunately, this is assigned time for us, so I cannot change that. We'll stick with that. So in terms of the remaining classes, this is a plan. Any questions? If not, let's get to the lecture. Today we're going to finish up the lecture on optical constants, and then we'll move on to talk about various kind of light responses, light matter interactions. So let's look at optical constants first. Okay, we talk about the complex, the complex index refraction. Okay, we have the real part, which is a normal index refraction that you probably have already known. And then the imaginary part, we call it extinction coefficient, okay, N and K, or N and kappa, just so that we can make a distinction with the wave vector symbol, okay, N and kappa. Okay, now in general, both these two quantities are frequency dependent, or basically wavelength dependent. Depends on the wavelength of the light. Okay, so if you plot these constants N and K as a function of the wavelength, now you can get the so-called dispersion relationship. And you can also say this is a spectrum. Okay, you can use both the classical and quantum theories trying to understand the dispersion relationships. And classically, you can use this Lorentz oscillator model we talked about earlier. When we talk about the dielectric properties of these materials, you simply extend it to frequencies in the optical frequency regime. That's a classical theory, and there are things that you can actually use this classical theory to understand the properties of these materials. But in general, to be more accurate, you have to use the quantum theory. And so, for example, as shown here, this is the N and K, real and imaginary parts of the complex index refraction as a function of the photon energy for amorphous silicon. Now, amorphous silicon is kind of like a silicon, but you don't necessarily have a long-range periodicity, so it's not a crystal. And the silicon atoms, you still have a little bit of sort of local ordering. So locally, silicon may still bond with 3, 4, or sometimes 5 neighboring atoms. So you still have some sort of local ordering, but you don't have a long-range ordering. Okay, so there's no periodicity. And then oftentimes, there's a lot of hydrogen inside to terminate some of these unbounded silicon electrons. Okay. Unfortunately, in this course, we are mostly going to be talking about crystals. So amorphous materials is going to be an advanced topic, and that's not part of what we are going to talk about here. Anyway, for this material, shown here are the N and K spectrum as function of photon energy. And you see that, especially if you look at the imaginary part, and then compare that with the classical Lorentz oscillator model, there are some similarities. In the case of Lorentz oscillator model, you see a peak. Now, obviously, in that case, this peak is symmetric with respect to the resonant frequency, omega 0. Here, as you see that you kind of see a peak, it's not necessarily symmetric, but you do see sort of it going up and going down, okay? And so there's some similarity, there's some success with this classical theory. And then you see the N value, so goes up and down. And now what's being plotted here, this is the polarizability. So you have to convert the polarizability to the dielectric constant, and then you take the square root of that to get to index refraction. So not necessarily comparing things directly, but you see that when you have the real part go up and down, the index refraction should also go up and down. Okay, so again, using the classical theory, you can explain it a little bit. And for example, if you look at this index refraction change on this side, whenever the imaginary part gets to a maximum, you're going to have a significant reduction in the index, the real part. And also on this side, very far away from resonance. So let's say frequencies photon energy very low, then that means this material, well, last time we also talked about how this imaginary part, the extinction coefficient, scales with the absorption coefficient. There's a relationship between the absorption coefficient alpha with this imaginary part. So in this range, when K or kappa is 0, the absorption coefficient is also 0. That means this material is transparent. So in this range, away from resonance, essentially, resonance is, you can think it's at this frequency, you have a resonance. They're very far away, so it's in this portion. Now, basically, you are looking at this portion of the polarizability, and then you can determine, so just use this classical theory, you can see that the imaginary part is almost 0, and you have the real part, and then it has this kind of wavelength dependence, okay? And so that gets you to the so-called empirical Cauchy's equation. It shows that even for transparent materials, that means that the imaginary part is 0. So the imaginary part of the dielectric constant is also 0. So it's basically a transparent material, but in that case, the index refraction is still wavelength dependent. It'll have this kind of dependence, and then this can be obtained from this classical Lorentz oscillator model. You just have to do a Taylor expansion on this to obtain this kind of empirical Cauchy's dependence for index refraction as a function of wavelength. So there are some good use of classical theory, but obviously you see that this peak, you may use multiple peaks to represent this overall dependence of the imaginary part as a function of photon energy. But that might be too complicated if you have to really accurately represent this overall behavior. So, but the other thing classically is that because the real and imaginary parts of the dielectric constant come from the same complex number, so since they are basically effectively integrated with each other, they are not fully dependent of each other. So actually, as I mentioned, every time you see a significant peak for the imaginary part, that also corresponds to a significant change in the real part as well. Okay, and this is so-called Kramer's chronic relations, and actually they are using these integrals. You can relate the imaginary part to the real part, or the real part to the imaginary part, or vice versa. So this is just for your information. This is not required. Just understand that the real and imaginary parts are not independent of each other. Okay, there are some dependencies. All right, so how do we use these index refraction to understand or to predict the light-matter interaction? And obviously, we know that when light is shining onto some material, there's a chance that a portion of the light may be reflected back, and the light may be may be able to go into the material with some probability. So the question is, what kind of geometric relationships can we obtain? And also the next question is, what's percentage of light that be reflected versus refracted? Okay, so there's a so-called Snell's law. For reflection, it's simple. The reflection angle is going to be the same as the incident angle. And here, the angles are defined from the normal direction of the interface. So this is interface between one medium versus another medium, and then this is a normal direction. So the incident angle for optical incidence is defined as an angle from the normal direction. In some other situations, the angle may be defined as angle from the surface. Okay, so it depends on the situation. In this case, as we measure the angle from the normal direction, so if we have a normal incidence, then the incident angle will be 0. Okay, so for reflection, the reflection angle, again measured from the normal direction, is exactly the same as the incident angle. So we have so-called mirror reflection. Okay, now for refraction, the angle, the refraction angle may be different from the incident angle if the two sides have different indices of reflection. Okay, so and there's a very simple relationship called Snell's law that governs what kind of refraction angle you will have. It really depends on how the index reflections are different. Okay, here mu, this is the this is actually the v, not mu. This is the velocity of the light wave. And remember, the velocity in the particular medium for the light wave is inversely proportional to the index reflection. V is the speed of light in vacuum divided by the refracting index. Okay, so so we have this relationship, and then you can also rewrite it to be a very straightforward n times sine theta is constant across the interface. Okay, n times sine theta is constant. So if you have a normal incidence theta 1, the incident angle is 0, then theta 2 will be 0 as well. So it's still propagating in the normal direction. So in that case, the light wave doesn't change direction at all. However, if the angle is not 0, then if you are going to from a low index medium to high index medium, as we have shown here, then the refraction angle will be smaller than the incident angle. That means if n2 is greater than n1, then theta 2 has to be smaller than theta 1, just to maintain n times sine theta being constant. Okay, so this is okay if we have light incident from low index to high index. The refraction angle will always be smaller than the incident angle. So the incident angle can be anywhere from 0 to 90 degrees, and then theta 2 will be from 0 to some number. Okay, some number less than 90 degrees. Okay, so that's okay. There's no strange things happening. But what if we have n2 being greater than n2 being smaller than n1? So we basically have going from a high index medium to a low index medium. If n1 is greater than n2, then theta 2 has to be greater than n1. So it has to. So if you have 0 degree, you have 0 degree as well. And then if you go all the way up, at some point, the angle of theta 2 may get to 90 degrees before theta 1 hits 90 degrees. Okay, and that means that light comes in this way, and then the refraction angle will be 90 degrees. So it's basically going to be propagating along the surface. Okay, so that's what's being shown here. All right, so we have this. Let me move this up. So we have this so-called critical angle, and then you have a reflection. You're still going to have reflection, but the refraction will be going at 90 degrees. Okay, but now what if, and this angle obviously is determined by the contrast between the index of refraction on either side of the interface. What if now the angle is greater than theta c? Okay, so we're still going to have reflection. The reflection angle, and the incident angle will be the same. What about the refraction? Then, if you have theta 1 is greater than theta c, then n times sine theta will be greater than n2. So you can't find the answer, a solution for theta 2, because we know sine theta will be no more than 1. So that's a problem. And this is so-called a total internal reflection. That is, we don't have refraction at all. So for this theta c, the critical angle, if you follow the math, when theta 2 becomes 90 degrees, you can solve for theta c. It's basically oxide N2 over N1. Remember, in this case, we're talking about N1 being greater than N2. So this ratio is less than 1, and that means that if you do the oxide, you can find a solution, okay? So in that case, this is for theta 3. But what if we go to a higher angle than that? Then basically light cannot propagate into medium 2. You only have reflection, you don't have refraction, okay? So there's only reflection, so we have something called total internal reflection. There's nothing going into medium 2. It's only staying in medium 1, the original medium where we have the light, okay? And remember, in this case, it has to be that N2 being less than N1. So going from high index medium to low index medium. Like if you have light going from air to water, water has high index, air has low index, air index is about 1, water is 1.3. So we don't have total internal reflection. But if you start the light from inside the water, and when the water comes up, then it may be reflected backward instead of getting up. Okay, so this is the situation where we have this total internal reflection. So this is being illustrated here. If the angle, the refraction angle will be greater than the incident angle, so basically the light wave becomes more deviated from the normal direction. And when it gets to the critical angle, the refraction is going to be along the surface. You still have reflection, okay? Refraction is going along the surface. And when you go to greater than the critical angle, then there's only going to be reflection. There's no refraction. Okay, that's a bit difficult to spell, to pronounce these two words differently. So I'm exaggerating that a little bit. All right, so this is total internal reflection. Okay, this happens from high index medium to low index medium. Okay, now there are obviously a lot of usages of this properties in many of these optical systems. People utilize this behavior to help manipulate the light wave. And then one of the other commonly used system you may not realize is optical fibers. As I'm talking here, how the signal is transmitted to you? Well, very likely there are optical fibers in between from here to Orlando, to Miami, wherever you are. Okay, we have optic fibers connecting us. And the way that these optical fibers work is that they're basically very, very tiny wires of glass, very, very transparent glass, extremely transparent. We'll talk about how transparent these materials are probably in the next lecture later today. But these wires allow the optical signal to be transmitted over long distance. That's because they're transparent. But at the same time, the design of these fibers also allow the light to be confined within the fiber. They don't leak out. Okay, if I inject the light at one end, the light will go out from the other end. Okay, you probably also see the use of these fibers on Christmas trees. They help guide light. So how does it work? Obviously, there are two things. One is the guiding of the light, and the other is the transparency of the light. Okay, we'll talk about transparency a bit later. But let's first look at the guidance of the light wave through the material. So this is a typical structure of a single mode fiber. There are other kinds of multi-mode fibers as well. But in this case, let's first talk about single mode. Okay, the multi-mode fibers will be bigger in the core. So this is the core, the 8-micron diameter for the single mode fiber. Multi-mode fiber can have this core diameter being tens of microns or hundreds of microns, so that they can have a bigger throughput of light wave. But for these single mode fiber, the diameter of the core is very small, 8 micron, and that's glass. Okay, and there's also cladding, right, surrounding that, maybe up to 100 microns, and then on the outside there's also buffer and jacket, so that we can actually lay out these fibers in the environment, even in the water, and we are not going to have damage to the core. Okay, so these are just protective layers. So the function of the guidance of the wave guiding is really happening at the interface between the core and the cladding. And the cladding is also kind of glass, but slightly lower index refraction than the core. the refraction index difference is very small, 1.5% basically. But that little difference is sufficient to help us confine the light wave. And by the way, for typical optic fibers that we use now, the wavelength, the light wave being transmitted through the optic fibers has a wavelength of 1.55 micron. So this is in the near infrared spectral range. Okay, we'll get back to this wavelength a bit later when we talk about the transparency of the fibers, because obviously whether these materials are transparent or not depends on what kind of wavelength we are talking about. All right, so now let's look at the guiding aspect. Okay, so we have a core, we have cladding. Okay, and so if you have a wave propagating inside, and because of the little difference between the index refraction of cladding and the index refraction of the core has slightly higher index refraction. So there's going to be a critical angle for total internal reflection. And if you do the math, the cladding 1.46, core 1.48, and take the oxide, that gets you about 81 degrees. So that means that if the incident angle at this interface, theta, as I'm shown here, is greater than this 81-degree critical angle, then we can have total internal reflection. Okay, so that means that, well, you have a little bit range. Okay, you have about 10 degrees or 9 degrees of range, so that the light wave has to be basically propagating along the axis of the core. So it's basically propagating forward, but it has a very sort of shallow impinging onto the core cladding interface. And as long as that is the case, this incident angle is greater than 81 degrees, the light wave will be reflected back. And once it's reflected back, it'll get to the other side, and this incident angle will be the same. Okay, and then you can still have total internal reflection. Okay, so with that condition satisfied, then you can have the light wave propagating as long as it can, until it's sort of attenuated because of the remaining scattering or absorption that we have in the material. Now, I do have to caution that this we call ray optics. Okay, we are looking at these light waves as rays. Now, that ray optics sort of this is going to be a sort of simple understanding of how fibers can guide the light. But in reality, this is not accurate enough. Okay, these are I call single mode, because what's the wavelength? 1.55 micron, and this core is only 8 micron diameter. And so in that case, we actually have to use wave optics. Ray optics is not sufficient to fully understand the guiding capability of optical fiber. But for this course, this is sufficient. Okay, ray optics is sufficient. Just looking at the total internal reflection, you can understand how fibers can guide the light. Okay, and obviously for the development of optical fibers, there's a Nobel Prize awarded to Charles Cao in 2009. There's a statue at the Chinese University of Hong Kong, which I visited a few years ago. And he basically, back in the 60s, laid out the fundamental theory of optical fibers, and then that leads to where we have now. We can have this long-range optic signal transmission that enables internet and many telecommunication sort of applications that really enrich our life. Okay. So the other thing related to optical waves, you also have to pay attention to so-called polarization. Now, this optical polarization is different from the dielectric polarization that we talked about in the previous chapter. This optical polarization is really looking at the direction of the transverse electric field. Remember, for light wave, the E field, electric field, is always perpendicular to the directional propagation. And so with the directional propagation, you can define two independent perpendicular directions. And so depending on whether the light wave, the E field is, you can have different kind of polarizations. Okay, so if you have these two different sort of perpendicular directions that you define X or Y, you have two partial waves. And if these two partial waves are in phase to each other, then the overall electric field is going to be basically, if you look at the sort of in the plane perpendicular to the propagation direction, then the E field will basically, seems like it'll be just oscillating back and forth along that direction. In this direction, going back, and then in the opposite direction, and then it'll be just in that plane. In this case, we call it linear polarization. However, if these two partial waves are, let's say, 90-degree out of phase, but they have the same amplitude, then at one point the total E field is going to be pointing. So when you, for example, start here, okay, at this time, then E field is going to be the Y direction is 0, then X direction gets the maximum. So you have the total E field pointing in the X direction upward here. A quarter period later, the X component goes to 0 and the Y component goes to maximum. So apparently the total E field is in this direction. So it's as if that the E field is rotating in this plane with a circle. Okay, we call it spherical polarization. And then if these two components are less than 90-degree out of phase, or different out of phase by not 90-degree, but let's say 70, 50 degrees, or let's say if the two components do not have the equal amplitude, then we have in general so-called elliptical polarization. And when you have many these different kind of polarization altogether, you can have a so-called unpolarized situation like a sunlight in general. The sunlight coming down is not polarized. But once it's reflected off certain object, it could be polarized in certain way. We'll get to that in just a few minutes. All right, so with these two polarizations, now if we look at the light incident onto a certain interface, okay, in that case, we have a plane defined by the incident and refracted light as well as the refracted light. Okay, so all these three waves, these three rays, now we are using ray optics at this point, can define a plane. We have this interface. This interface is perpendicular to this plane and this normal direction, and these waves and these two incident refracted waves define a plane. We call that incident plane. Okay, so that incident plane is perpendicular to the interface. All right. So with respect to this incident plane, now we can define two perpendicular directions for the E field. Okay, so this is a directional propagation. So the E field can be perpendicular to this propagation direction, but it could be in this plane or it could be perpendicular to this plane. So basically going in and out. Okay, so these are the two different polarizations. Okay, and then one is called S, one's called P polarization. I think these words came from German. These symbols came from German. So the P is parallel, not perpendicular. P is parallel. Okay, parallel means it's in this plane. So that's the P polarization. Is incident in this plane, and the S polarization is perpendicular to the incident plane. So it's basically think about perpendicular to this direction, perpendicular to this direction, and so it's going in and out of this plane. Okay, this is P, and S is going in and out. I can illustrate it here, but you can imagine that. Okay, so these are the two different polarizations, and actually the percentage of light reflected back or the percentage of light going through this interface actually does depend on whether you have S or P polarization. Okay, so we call this reflectance or refractivity. This is the percentage of light intensity, basically power of light being reflected at this interface. And this reflectance for the S wave, for the P wave, we have these two equations. These are so-called Fresnel equations. And you see that the parameters involve the N1 and N2, the index refractions on both sides, indices of reflection on both sides, and also the incident angle, theta I, and theta, well, it's only theta I, but once we know N1, N2, and theta I, you can determine the angle on the other side, the refracted angle, okay? You can determine theta T as well. Okay, there's theta T here, okay? These reflectance are calculated based on the so-called boundary conditions for these electromagnetic waves, which we're not going to go into these details. I'll just give these equations so that you can make the calculation. Okay, and knowing N1, N2, and knowing what kind of theta I you have, you can calculate theta T, and you can do the overall calculation for the reflectance for S wave or the P wave, S polarization or the P polarization. Now here, just a little bit more. This reflectance is the intensity ratio, intensity of the refracted wave versus the intensity of the incident wave. And then following electromagnetic theory, we know the intensity is proportional to the square, the absolute most square of the E field. of the electromagnetic wave. And then you can also define a so-called refraction coefficient by looking at the ratio of the E field. And then when you take the square, mode square of that, you get to refractance, okay? So those are the different refractance for S wave and P wave. And if you do plot it, let's say assume N1 is 1, N2 is 1.5. So this is air, for example, and the N2, that's a glass. Glass in the visible spectrum range has an index of 1.5. So this is a situation for light incident onto a glass surface, okay? And you see that this is, horizontal axis is the angle of the incidence, the incident angle. So there are a few features that you can see. First of all, for normal incidence, the theta I is 0. Then you see the RS and RP are the same. And then you can reduce it to theta I is 0, theta T is 0. So it's just N1 minus N2 over N1 plus N2. So it's a very simple relationship. Okay. And then if you do the math for 1 and 1.5, this come out to be about 4%. That's why we have 4%. Again, so if light is incident onto glass, on the front surface, it'll lose 4% of light to refraction. And once the light goes into the glass, let's assume glass is perfectly transparent, then there's no attenuation for light to get to the back surface of the glass window. And at the glass back surface, then you just reverse N1 and N2. So again, you are going to be seeing 4% refraction. So you have 4% off the front surface, 4% off the back surface. But obviously, the 4% on the back surface is really 4% multiplied by 96%. Okay, but roughly that's still 4%. Okay, so essentially, if you think about light wave transmitting through a glass window, you're going to lose about 8% of intensity. So you only have 92% of the light can actually go in if you don't do anything. Okay, just assume it's a single piece of glass. Then that's the amount of light you will lose because of refraction. Okay. We'll get back to the refraction loss a bit later, but looking at this dependence of the refractance as a function of the incident angle, you see that for the S wave, remember the S wave is a wave with the polarization perpendicular to this plane. Okay, so it's going in and out. The E field is going in and out. Okay, and in that case, you see the refractance just monotonically increase with the incident angle, and eventually it'll reach 100%. When incident angle is 90 degrees. So that means that you're really sort of skimming over the surface, okay? Incident angle being 90 degrees means you are really incidentally along the interface. So nothing's gonna be getting into the second material. Everything is gonna be refracted back. It'll just stay in the medium one. That's why you have 90 degrees. At 90 degrees, you have 100% refractance. So it's a monotonic increase for the S wave. For the P wave, eventually, you also get to 90 degree angle. You have 100% refractance. Okay. However, somewhere in the middle, as early on, the refractance actually goes down with the incident angle, and eventually can reach exactly 0 at some angle. We call this called Brewster's angle. At this angle, the P refractance, the P wave refractance for the P wave will be 0. And remember, the P wave is oscillating in this way. Okay, so and the reason that once it hits somewhere close to the interface at some angle, the boundary condition dictates that the refractance will be 0. Again, we're not getting into details, but just remember that it is possible that for the P wave to have 0 refraction. So all the P wave is going to go through. That means at that point, only the S wave can potentially be refracted. Okay, but eventually it'll also climb to 100% with 90 degree incident angle. Okay. Now, if you think about, let's say we have a 30% of light refracted, then remaining 70% will go into the medium, and we call that transmittance. But this transmittance is the transmittance through this interface. It's not transmittance through a material yet, because if you're transmitting through a material, there's a back surface you have to also worry about. This transmittance is only transmitting through this interface. Okay, so similar to the refractance, when you define the transmittance, it's the percentage of light intensity being transmitted through that interface. And obviously, R and T, the sum should be 100%. Okay, when you add them up, you get 100% because we are not losing energy at this interface. So looking at the Brewster's angle, as I mentioned, at this Brewster angle, the P wave refractance will be 0. So this angle has special usage, special features, okay? And you can try to figure out when that angle is 0. So this is the equation for the P wave reflectance, and that means that if, when you get to the top, the numerator being 0, you have a 0 reflectance. So that's how you can determine what angle you're going to have. And remember, the incident angle and the refraction angle has obey the Snell's law. So if you do that, you can actually obtain what kind of Brewster angle you will have. Basically, the tangent of the Brewster angle equals N2 over N1. And in this case, remember, N2 is greater than N1. So this is actually greater than 1. So that means the Brewster angle is greater than 45 degrees. But the tangent of that is the ratio between these indices. Okay. And so this theta P is called the Brewster's angle, or you can also call it polarization angle. And the reason called polarization angle is that, well, actually for this Brewster angle, there's also a simple relationship between theta I and theta T. The sum of that is 90 degrees. Okay, so essentially, you're coming with both S and P waves. And then at the Brewster's angle, you have S wave partially reflected. You have the P wave going in through completely, and then obviously the S wave will go through as well. So the reflected light will have both S and P waves. So remember, S wave is going in and out this plane, P wave is oscillating this way. And for the S wave here, for the reflected light, you only have S wave. So it's now it becomes so-called linearly polarized. There's only one particular direction. It's always going to be in that direction. That is perpendicular to this plane. Okay, and by the way, this direction, this angle is 90 degrees between the reflection and the refracted light. Okay, and actually this is why that I mentioned that even though the sunlight is unpolarized, there's no preferential orientation for the electric field. The electric field can go in every direction, but once it's reflected off certain object, you can possibly have linearly polarized light, and so you may actually see these glares with reflection of certain things, and that's why you sometimes you want to wear polarized sunglasses to help reduce glare. So this is an exercise for you to find out exactly how these polarized sunglasses work. It's related to the fact that the reflected light can possibly be linearly polarized in certain cases, if the situation is correct. All right, so now we talk about reflection, right? In certain cases, the reflection is not good, okay? And for example, if we think about trying to harvest sunlight and trying to heat up things or convert it to electricity, like using solar cells, and silicon is the major material people use to absorb sunlight and trying to convert to electricity. We'll talk about that next week. And for silicon, if you remember, the index refraction is pretty high. The dielectric constant is 12. So if you take the square root of that, you can get to index refraction of 3.5. So if you plug in these numbers, then the light incident onto a surface of glass, a surface of silicon, and normal incidence, you're going to have 31% reflection. And for the and if you go to some higher angles, and just like what you see in the plot earlier, this reflection can actually be even higher for at least for the S wave. And when you go to a really large angle, that reflection can be close to 100%. So in that case, obviously you're losing a lot of light to reflection, and this is not good for light harvesting. And in this case, people develop so-called AR coating, anti-refraction coating, trying to minimize the reflection. And the simplest AR coating can just be a thin film, okay? A layer of material, a thin film between air and the medium. Okay, so in this case, the opportunity comes up that we can rely on so-called interference. And if you want to reduce the reflection, then you want to have these reflected light destructively interfere. So the way to achieve that is now you think about the light incidence onto the AR coating. There's going to be a partial wave reflected. Some other waves are going to be entering that medium, but then once it hits the back surface of the AR coating, this is the interface between the AR coating and the semiconductor, then you're going to have another reflection. So think about this A and B partial waves. If these two waves can destructively interfere, then these waves can cancel each other. So the only energy is going to go into the semiconductor. So all the energy will go in. Okay, so how do you achieve a destructive interference? Well, then the way to achieve that is that the phase angle between A and B will have to be 180 degrees off, pi, 3 pi, 5 pi, that, okay? And the phase angle change is really concerned with how thick that material is. Basically, the phase angle is k times the wave vector times the distance, right? Kx, okay? So the k, we know that in this medium, k will be increased by a factor of this index refraction, okay? And so basically now you have this is a wave vector, 2 pi over lambda. This lambda is a free space wavelength multiplied by index refraction. This will be the wave vector inside this medium, multiplied by the transmitting distance. It will be d, and then you're coming back, so the 2d. Okay, so k times x. Okay, that's the phase angle change associated with that travel. Okay, that extra trip for b. And so when that phase angle is 1 pi, 3 pi, 5 pi, then A and B wave can destructively interfere. They have to be at least have the 180 degree off, but then we can have a periodicity of 2 pi. So that's 180 degree plus 360, that's 540, and so on. So it's pi, 3 pi, 5 pi, and so on. So as long as the extra phase angle change for the B wave to go through that full cycle in the AR coding is 1 pi, 3 pi, and so on, they can get to a destructive interference situation. So D is basically 135 times a quarter of the wavelength. And remember, a quarter wavelength is actually a quarter inside this medium. The wavelength inside this medium will be shorter than the free space medium. Free space meaning in vacuum. Okay, so in free space, it's a quarter, lambda over 4. Once it's inside the medium, it'll divide that by the index refraction. So lambda over 4m. That's it's a quarter wavelength inside. A quarter, you have half pi. Another quarter, you have another half pi. So that gets you a pi. Okay, and then you can multiply by 3. So it's a 1 quarter, 3 quarter, 5 quarter. Those are the thicknesses that will give you the destructive interference. But at the same time, to completely cancel out the intensity for the refracted wave, you have to make sure that the reflectance, the amplitudes are the same. Okay, and then you really have to look at the refraction coefficient at these two interfaces. Okay, the refraction is basically dictated by the ratio between the index contrast and following this relationship. So if you want to achieve the same refraction coefficient, then actually, throwing away the math, you can get to the index refraction of this material should be the geometric average of the indices of refraction of the two medium on either side of the AR coating. Okay, so those are the two requirements on the thickness and also on the index of refraction. And obviously, once you determine the index of refraction, then you can also plug it in here to determine the actual thickness. Okay, so really the AR coating works to minimize or to eliminate the refraction. Okay, anti-refraction. That's the name of the material. Okay, and that allows most of the energy can go in. But now the issue comes in that, let's say, in the case of harvesting sunlight, right? Sunlight spectrum is very broad, so you're not dealing with one wavelength. Okay, so if you have a particular wavelength, then you can figure out what is the desired index of refraction and desired thickness to achieve perfect cancellation of the refracted wave. But now when the thickness is already set, when the material is already set, when you go to a different wavelength, then the destructive interference condition may not be satisfied at that time. Once simply, I mean, especially for this D, once you change the wavelength, the phase angle is no longer going to be exactly pi or 3 pi. It'll be off a little bit. That means the cancellation will not be perfect. So you can achieve perfect zero reflectance for some wavelength. When you go to different wavelengths, the reflectance will be non-zero again. And then also, what about the angle, incident angle? This is only for normal direction, but that's only one special situation. When you go to other angles, again, you're going to see a non-zero reflectance. So actually, how to develop a broadband? Broadband means many different wavelengths. Broadband, wide angle AR coding. This is actually a very active research topic. Now, on the other side of spectrum, we might want light to be completely reflected back, like we want to have mirrors, okay? Traditionally, we use metals, shiny metals, to provide this mirror function, but metals do have some final conductivity, okay? And then so this is something we're not going to talk about too much, but if you have a finite conductivity, that means when the electric field is oscillating inside these materials, that could be Joule heating. Okay, you have E field, that means you move the electrons around, and you have finite conductivity. Then you have finite power consumption. So the mirror reflection is not 100%. Okay, there's some loss. Now you do have the opportunity to use dielectric materials, transparent materials, to achieve a perfect reflection. And the way to achieve that is to use so-called dielectric mirror. You have this is one example. You have alternating stacks of two different materials, N1 and 2 with different indices. And let's just assume N1 is less than N2. And when you do these stacks, and for each layer, you control them to be a quarter wavelength thick. So a quarter wave, and we also call that quarter wave stack. Okay, and then remember, because the index refraction is different, the corresponding wavelength for the same incident wave will be different as well. Lambda is the free space wavelength divided by the index refraction. Okay, so if you have smaller index here, either the thickness will be slightly greater. But regardless, as a light wave propagates through, you have quarter wave, so that means you have half pi phase angle change. If you reflect it back, well, when you have this interface, you reflect back, then the incident wave and the reflected wave will see pi phase angle difference. Now, think about the wave going into medium 2 and then reflected back. So now this reflection, again, is going to cause extra pi phase angle difference. You have pi here as well. You have extra pi. But now for this wave, you go in, for this blue wave, actually you have to start with here and then end with 0. So you have actually 2 pi phase angle change. Okay, pi in this material, pi in this material. For A, you only have pi. So that means you have pi angle difference. Well, actually, there's another pi angle shift. That is, if R12 is negative because N1 is less than N2, then at the 2 to 1 interface, the R21 is actually positive. Positive means that there's no phase angle change. If you have a negative refraction coefficient, that means there's actual pi. The E field actually has to reverse the direction. That means equivalently, you have actual pi phase angle difference. So you have pi plus pi here, and then for this one, you have 2 pi. So when it gets back to the front surface, both A and B has experienced a 2 pi phase angle change. And that means now they are in phase again. Same thing with C. Okay, so all these partial waves are going to be in phase. If they are in phase, that means we have constructive interference. Okay, when you have constructive interference, that means you are enhancing the reflectance. Okay, so for these kind of quarter wave stacks, you can possibly achieve perfect reflectance in some spectral ranges. Okay, and then typically use many layers to broaden the reflectance range. Okay, to maximize reflection. Okay, so this is so-called dielectric mirror. This is another way to utilize this reflectance to achieve a control on how you want to manipulate the light propagation. Okay, so we're already at 11:30, so let's take a 3-minute break. So we'll reconvene at 11:35. Trying to finish up the remaining lecture slides, and then that allows us to start our quiz at 12:15 on time. Okay, so let's take a few minutes break here.